boundary here, we have df by dt equals right hand side here, and we multiply everything with the right hand side with a profile that goes smoothly to 0 as we approach the boundary. So here we put a factor phi of x, and the straightforward interpretation is we change the time scale. So evolution is slower here because we multiply the time derivative. So we can write this as df by dt times phi of x. Well, don't look too closely at what I'm writing here, but you may get the idea, which is weird. But yesterday I discussed it with somebody, and it occurred to me that that's similar to what happens near a black hole if you look from afar. Waves go towards the black hole and they slow down and slow down and slow down. They don't get reflected, I think.
Yeah.
So there are ways of realizing that in reality, although you need pretty drastic measures like black holes.
I'm sure the referee would be convinced when you talk about black hole.
Depends on which community you're working
We
with.
put a tiny black hole at boundary of our
But there's actually a different way of interpreting this that makes somewhat more sense, I think. Typically, if this sort of border quenching is used or has been suggested in order to get non-reflecting boundary conditions for waves, which is difficult if you want to do it right, if you have many complicated different wave types like we have in MHD. And a typical wave equation looks like this. There's the time derivative of your state vector, variable vector, is some matrix times the spatial derivative, where this matrix for sound waves and for many types of waves has 0 entries on the diagonal, but the off-diagonal terms are different from 0. Sound waves, Maxwell equations, arithmetic waves, same story. There is other stuff that's not so important. And now if we multiply this with phi of x, then we can understand, we can interpret this as just replacing df by dx by df by d psi, where d psi is dx over phi of x. And this is a mapping between x and psi that effectively makes psi go to infinity as x approaches the border here, at least unless you choose the wrong drop-down here. So what we're really doing is we have the grid points like this up to the border, and we map that. We solve the equations where the grid points are like this, and the grid extends all the way to infinity. And so the waves have to travel all the way to infinity before they can come back. And so they never come back, ideally. In reality, they just stop getting resolved, and then one might need to use hyperdiffusion, maybe also just in that zone near the border in order to really get rid of them. But there's a simple test check in that's called spherical sound wave in the samples directory, where we played with that, and we just start with a pressure perturbation that propagates as a spherical sound wave, and surprisingly little of that wave is reflected from the boundaries.
That's true. I did that also. And the problem, and finally, the wave are damped because you lose energy on the border. And finally, and then it's very difficult to get normal modes in this case. You get normal modes only in very small time, and then the mode disappear very rapidly because you lose energy at the border.
Sure. I mean, if you have only outgoing waves, you can't get standing waves.
Yes, that's not a perfect outflow boundary condition.
It's not. It's it's a good radiation boundary condition. But if you want standing waves, that's of course not what you want. It yesterday occurred to me that it might be slightly better to not multiply the whole right-hand side with this phi, but only this one. And this we could simply do, well, I haven't tested that yet. This we could simply do by changing the derivative operator. Whenever we take the first derivative with respect to x, we multiply afterwards with phi of x. And it would probably be worth comparing the two approaches. It's similarly simple. We plug it into the machinery in one place, either in the spatial derivative or in the time derivative.
But you want to only multiply the linear terms with phi of x, or what terms? What does this m df dx actually stand for? Does that stand for the linear terms? All the linear terms?
Well, quasi-linear terms. M will generally be a function of f, but still, that's the. I guess you're asking what is this stuff here? This here is, for example, mu times or plus u or pi times plus CNT or whatever. So for the wave propagation is described, is controlled by the first spatial derivatives. And so those are the ones where we really want to have that factor. If we don't multiply the dissipative contributions with that factor, then we still have dissipation out here, which will probably help if we want radiative boundary conditions.
Actually, we just had something like minus alpha b when we are dealing with tiny blocks. We just yes, we just done by some diffuse force minus alpha b, something like that. It's not minus alpha gradient of velocity.
I mean that's a different approach. Yeah. Here, in a sense, we do everything inside the boundary. For the star in the box stuff, we basically add something outside. It's related but somewhat different, I think.
Was that about driving the value towards some specified value at certain times?
The outside the star, we just damp the velocity.
What is that called? I guess this is called sponge on you sometimes, right? What you were talking about here. I mean, we call it water quality, but it's what other people will refer to as a sponge. So
no, I think what Boris is talking about is sometimes referred to as sponge.
That's a sponge.
This thing here. There's a paper by Colonius and Ran, which I could dig out, and they discuss the approaches used by other people before, and they quote this sponge method. So they, at least the authors of this method, don't consider this a sponge method.
But it's the same kind of thing, it's linked to self-similar methods, because when you write this there is about physics, point inclusion, explosion. Physics, it's radius of the inside depending on the time. It's not exactly, but it's close to self-similar method we use for implosion or explosion.
I guess depending on, since we have the freedom of choosing a profile here that goes sufficiently smoothly to zero, but has no other constraints, I guess a number of other special methods can be interpreted in this light.
Yeah. No, simply it's so you can find this in Zaldovish, and you have this applied to a shockwave, exploding and imploding shockwave.
So we have heard here about two different ways. The first way was to say the f by dt is being replaced by the f by dt times an phi of x.
Phi of x maps out the boundary position.
The other method is to replace the f by dt by df by dt,
or rather the whole equation actually in this case.
So to replace this by df by dt is the right hand side, replace this by equal to the right hand side minus, and then that's what you mentioned, 1 over tau times again is phi of sigma term here. phi or phi of x or whatever, which maps out the boundary, times in f minus f reference, as I would call it. Now, and this one,
Well, actually, I guess that's 1 minus phi there. Because you only want to switch that on near the boundary.
what do you mean 1 minus? Oh,
The phi should be 1 minus.
okay,
phi.
yeah.
Or I feel the way.
Yes. Yes. Now this one we call a buffer, but is that the one which you call a sponge also? Or did you mean sponge this big?
I'm looking now to.
So anyway, this one we call buffer. Buffer zone. And Vladimir uses that. Natalia uses that extensively for her Newton star simulations. Brigitta von Jukowski used it for the wind simulations in 2003 and so forth. So we call it then buffer zone. And now the question is, what is the sponge method? The idea is that this is called sponge method or what? And you interpret, so this is perhaps sponge, I put it. And
Sponge layer, an additional damping term is added to the differential equation which neutralizes any deviation from the
then it would be this.
That would be your buffer.
Yes.
Yes,
What we
that's
call a sponge.
completely different. In the first case, you kill the dynamics, the whole dynamics. In the second case, something like with a relaxation method in the Boltzmann equation, when you put something, some relaxation term in your dynamical equation, that's radically different. And but I never saw buffer zone in the manual, right?
That's probably true. We discussed it actually the first time in the last Pensacon meeting, because then there were two users, namely Vladimir and Natalia, both of them used those, and they were not actually general parts of the code at the time. So there were Natalia's implementation of the buffer zone, not you but another Natalia, in which case it was in the so-called neutron star module embedded entirely. And then yours was entirely embedded where? What? Right. So these were really in the respective modules, and now there is a more general thing. That's actually.
But actually, I think that the manual is very weak on boundary conditions. It just describes what they are. Maybe we should give some more hints about what is practical or.
I think because, for example, the cooling term is,
Yes.
if we say, okay, now we can call that buffer zone, the cooling term should be replaced by buffer zone for entropy equation means cooling term finding. If we adopt the buffer zone, it's a generic term for relaxation term in the dynamical equation.
Well, if you work in temperature, that's true. If you work in entropy, then you have something that does not exactly follow that form. Well, okay, maybe the
That's
buffer
buffer
zone
zone,
is general enough. But then if other people call it sponge zone, but then you wouldn't use a sponge to damp temperature deviations, right? In real life.
What's wrong with that? I mean, that's still okay. We use this, and in fact, one of the first times in connection with the upper boundary condition for the temperature in convection simulations. We would still call it buffer zone then. Also was called an overshoot layer, of course, but is that not good?
I mean, if people refer to this as a sponge layer, then maybe we should make a connection with the
Okay.
nomenclature that's common. But if we call it sponge layer, then the term doesn't make much sense if you apply it to temperature.
But for temperature, it's a bit, for stratified runs and for the temperature, isn't this a bit problematic anyway? Because the value of temperature at the very upper boundary doesn't change. And so if you start out with a stratification that is sort of in the right ballpark, but isn't really, but you actually want the system to relax to a new state and expect the certification to adjust indifferently if you have ionizations and so on, then you're basically, I mean, you can never change the boundary value, which is a bit
Yes.
restrictive, maybe.
Right, but of course you can have a more elaborated scheme that is actually obeying some equations. So first of all, f of f ref.
Wait a minute, sorry, I thought we were talking about the border crunching thing. I mean, in the relaxation method, the boundary value actually does change.
What do you mean the relaxation method?
Yeah,
What is relaxation?
Well, what is sponge and what is doesn't know?
That's what I'm just
Sponge and buffer zone are the same, and that's the lower one. The Newtonian cooling
Oh, right,
applies to
okay.
temperature.
Oh, okay. No, I was referring to the border crunching, the upper one.
So even with the lower one, you don't change the reference temperature. So even though temperature can
Okay, yeah, right.
change on a short time scale, it won't change significantly.
But in the border crunching case, of course, the time derivative, the value doesn't change at all.
No, but ideally you wouldn't care much because the border is mapped to infinity. Although, unfortunately, you have only a limited number of grid points between the real points, physics points, and infinity, which means there is some.
This discussion is important for beginners. With that kind of discussion, we unify a lot of boundary conditions which are formally equivalent: cooling term for temperature, damping of velocity, and finally, in the manual, I think it's important to specify some kind of generic boundary condition, some kind of relaxation, or clarify the manual.
So this one has a name. This is what we refer to as border crunching.
Well, I guess we should check what Colonius and Ron call it.
Who?
The people whose paper this is based on.
Right. All right. We do that by lunchtime then, before we room for lunch. Maybe then we can check and come back to that. Whereas this method, either it's called buffer zone or sponge zone or relaxation method you use.
It sounds best as relaxation to my taste.
Because there's a 1 over tau,
Yes.
of course.
Or Newtonian cooling.
And it's a Newtonian cooling, but then f ref is normally actually 0 for the temperature.
0 Kelvin?
Yeah, or 3 Kelvin, of course.
Mathematically, I think it's a relaxation method is better from a mathematical point of view. Relaxation is really relaxation.
Maybe so. What do you think, Wolfgang? But anyway, it's up to, if the term sponge method has been in the literature for years, then of course it's a different thing. I actually heard it really I haven't really heard it many times. Good. And I made a note on this in the manual. Oh, I see. Damn it, look at this what happened.
You're not supposed to put that on when you
No, now I know that. What happened to the lens then? Damn it. Yes. Yeah. Need a new lens then.
Oh, that's already a technical question. Non-reflecting open boundary conditions. Is that what we've been talking about now? Non-reflecting open BC. Is that related to what we're talking about now? I guess so, yes. But I think
Maybe later you can clean the lens. Maybe later we can clean the lens.
Good point.
So should we write it on the Boxilla list that the manual should be expanded to describe boundary conditions and better and this kind of question? I mean, we have our wonderful Boxilla.
Yes.
And this could be called a bug in the menu.
The bug in the menu.
Well, many backtracks also accommodate requests for enhancement. So I will put that in now.
So what do you put put in?
That someone needs to update the menu on boundary conditions and describe it. We need to find good word for this and describe it in the menu.
Oh, and the Godzilla, yes, yes. Do people know what he meant by that? So we have, in the pencil code homepage, there's various entries, there's mailing lists and stuff, but there's also one page called Bugzilla. So that's where you can report bugs. And actually everybody. There's actually no user testing or something. So for example, this, we got completely external bug reports into that. So everybody can actually file a bug under Bugzilla. And then it's being taken care of, hopefully.
You don't want to use that thing.
We think we're going to see whether we can clean that, yes. Indeed, okay, there's another issue that we have, of course, the manual, which is is a LaTeX file, and it's put online, and it is under CBS. So everybody who has access to the development of the code also has access to actually changing the menu. On the other hand, if you just want to do something quickly, it is not so easy, of course, to do that. And it's much easier to change it under Wiki. And that's the reason why we have also a Wiki page. Now, it's not clear what should be added under Wiki and what should be added under the manual. Does anybody have comments on that?
I think the stuff which are more established have been used by people and stable can go to the manual.
Mm-hmm.
And things we are experimenting with and more or less how sure it works can go to the wiki. And then in the next meeting we can look at it and then settle about it.
Aha, that sounds like a good idea. So in other words, Wiki for temporary first comments.
And you think we can do some of this stuff is surprisingly non-temporary.
So how do you say this? A wiki for unestablished, for new.
Not so well established stuff.
Yes. Yes. So that was indeed one of the entries under the discussion list for the wiki and menu, wiki or the regular menu, and that has been done then. So that means good. It's now 12:30. We can go for lunch. Or maybe if somebody has some more comments of what we should discuss later in the afternoon after. So we have, in the afternoon we have talks then by Walker about CDS, and then by Swinger, and by Marcos. And then we have later in the afternoon the discussion.
We haven't really discussed the upwinding scheme in non-Cartesian coordinates. We've discussed the upwinding scheme, but
Yes. My understanding is that's what I
thought
can.
we did, but anyway, no.
no, you just introduced it. We didn't.
I mean, isn't the conclusion that so as Wolfgang was saying, upwinding means that we write Euler graph as in the form of Euler grad is our usual 6th order scheme, 6th order, plus an alpha times the modulus of the velocity times the 6th order hyperderivative. How do you say?
No, I think I understand correctly what Wolfgang is saying is basically that when you bring u dot grad in non-Cartesian, you have a factor of, for example, with u theta, you have a factor of 1 over r and stuff like that. But inside what you have is basically a finite difference. So you just change that finite difference from a centered finite difference to a centered finite difference plus something else, which is the upwinding stuff, right? And the 1 over r factor just remains outside.
Essentially, yes. I think we even don't need to do that because we need the 1 over r factor in the advection term as well. So I think it really just boils down to replacing the centered first order derivatives by centered first order plus delta x to the fifth sixth derivative.
Yes,
Like we are doing now. It's just we have the same factors for the advection term as for the additional.
yeah, so what you are basically saying is that a finite difference is a finite difference. You just change it from a centered one to a different one. And the scaling factor outside, which may vary from one point to another point, is
It's
a
the
different
common one anyway, yeah. Which actually
I'm not. I'm
Which
just
actually would mean that this should have worked out of the box, and Boris is saying it did not.
I just have one comment on that. When you are doing it in non-Cartesian, you have not only the derivative, but also another term which is not a derivative, which is coming from the Christoffel symbols. I mean, u dot grad will come as not only a derivative, but also you can be just kind of one term which will be just dimension of 1 over L, but not a derivative at all. You see what I mean?
I have a faint.
But actually, you see what I mean.
I have a faint idea.
See, when I am taking a derivative in the non-Cartesian frame,
Yes.
non-Cartesian coordinate system, I have a derivative and then something else which is coming from the Christoffel symbol, which will not be a derivative at all, right? So this u dot grad will have something which is a finite difference plus something which is not a derivative at all.
Yeah, it could be the value of the function, for example.
Yes.
But I don't think we need that
Yeah, but-
for the upwinning. But this is one way of interpreting upwinning, but maybe this is actually misleading. If you go back to the motivation, we have the choice of using a centered stencil for calculating the first derivative or using a different stencil. And if we really use an upwind stencil by discarding one of the points, then that's still an approximation to the first derivative that we calculate all over the place, be it in spherical coordinates or in torus coordinates or in Cartesian coordinates. And that asymmetric stencil has the property that in Cartesian coordinates it stabilizes the advection term, and I'm pretty sure it will do the same thing in all coordinates.
I agree. My difficulty is more conceptual. See, when I'm the derivative, basically I take a difference and then take a limit. So to take the difference in non-Cartesian frames, I am doing a parallel transform. And that's what is being signified by the this gamma coefficients. Right? So I'm not sure that that property is being preserved by this, whether it's remain a derivative at all in a way.
So, how about the following? Sorry.
Well, my view is nobody's telling us how we have to calculate the finite difference approximation to the derivative, unless we want to have some conservation properties which are violated with that, as Tobias told us. So why can't we just, instead of using the centered stencil for doing the phi derivative, the theta derivative, the r derivative, use the upwind version? All we lose is 1 mark in order, because that's only 5th order. I forgot to mention that, I think, instead of 6th order, and that's it. It'll have the stabilizing properties, I'm pretty sure, and it's just one out of many, in a sense, equivalent ways of approximating derivatives by finite differences.
I mean, what can, when you compute the upwind derivative, do you, I mean, if you compute the central first derivative, do you take 3 points on each side of the points where you want to compute the derivative, but not the point itself? But for the upwind derivative, you actually do take that point into account, right?
Yes.
So then you also have 6 points, because you have 3 in the upwind.
Yes, but you still only get 5th order, because the symmetry somehow helps with the centered.
Oh, I see. Okay.
Basically because, if you have a central scheme and you have polynomial of order 6, you get 0. And you have x to the 6, you get 0. So that's the symmetry of x to the 6 together with the antisymmetry of the scheme somehow gives you one order of 3.
So how is the following?
Just, sorry, I have a question. I didn't understand. So you take the point that, for example, when you are in 2D, you can apply it on a square. Or you see, you are not, and it's very important the points you take, because we have tested with this kind of approach that for a star you have to really pay attention. You can use any points. If you take, you have some direction to.
The tensor code evaluates all the first order derivatives separately. So we do the x direction, we do the y direction, we do the z direction. For each of these directions we have the velocity.
No, I'm speaking if you are in r and theta.
Okay, we have the r direction, we have the theta direction, we have the phi direction.
Okay.
And we don't mix those. We take the r derivative multiplied by ur, we take the phi derivative multiplied by omega, or some sine theta factor. We really do them separately.
Okay.
So that's only one way of doing it, basically.
Okay.
No ambiguity.
That's right. Now, maybe, so if you do, so my suggestion is to do the following. If you answer spherical geometry or any other geometry, our operator, which is, for example, this, is of course written as ui times f comma I. And of course, it's not comma but semicolon. And if this is a vector, then let me write this in a different way. Let me write j, and I. And that's the I component of this whole thing.
So we're supposed to distinguish I, semicolon, and j, right?
That's what you're supposed to distinguish it. And that is equal to this times fi comma j minus. And everybody know this now? So we have another uj, of course, because nothing happens here. And we have.
No, you don't think you have uj?
Yes, you just
Oh, sorry, sorry. Okay, but not fi, right?
No, not
You
fi.
have
Some if
fa
k.
or something.
Some if k, if gamma I k.
You mean, like so, right?
Some, no, yeah, and then some we can.
Is that correct, by any chance?
It cannot be.
It cannot be right. This is of course L. And this is, what's the other one then? This is J. No, it's correct. Right. So my suggestion, so obviously there's no derivative on this one at all.
Yes.
There's a derivative on this. And for us, we know how to do that. That means, so if you are in our spherical vectors, it means this is u, let's write this down as a, so this would be ur, I write it with a hat, but for r hat, it's the same as ur itself. And it would then be times df by dr hat. So that's like this we can, and then minus it down, of course.
R hat is not so interesting.
Oh, it's not so interesting. So here, but then we have additional terms. Plus u theta hat times df by d theta hat. And so forth. So in 2D that would be all we need to do. And that of course is nothing else but just the u theta times df by d theta times 1 over r. So the idea then is simply to use the upwinding derivative straightforwardly. So don't think about anything. Just make sure that the 1 over r factors are correctly in place. So we just use a hyperderivative as it was out of the box. And if we are lucky, I mean, these the 1 over r terms should automatically be taken care of course. That's what. So the return, the output of the derivative routine, or the DAB routine, I think it's called, right? Derivative. It's that, yes. So the output of that is already correct. That is taking care of these factors. You have to be slightly careful with the mixed derivative, and that one is called their ij, right? So there, I think it also has the R factors correctly, but you have to remember that there would be additional factors if you interchange two derivatives. So that means f comma ij is not the same as f comma ji, because there would then be an extra term from differentiating 1 over r terms, for example. These bring extra terms. This we have done, of course, correctly in the corresponding routines where this is used, like for example in the double curve. If you do the double curve, for example, then it's in that routine where this is being corrected. The point is simply these two things would be almost the same, except for an additional correction factor. So we don't want to calculate it twice. So we really only calculate it once and do the correction afterwards. So I think that actually was a good session in the sense that we actually also came up with some real suggestions how to solve the problem for us.
Yeah.
So I think we have found a solution here then. This that Duba also thinks that is good and Wolfgang thinks, right?
Yes. As a third derivative is not, there is no problem. It's you grab something, actually it's good.
Yes.
Problem is with upbringing.
No, that's we treat it as an upbringing thing then.
I think the reason why upbringing didn't work out of the box is because we really do something like this. But if we just write for the first derivative df by the, I don't know, psi. Psi can be x, y, z, theta, whatever you like, as standard, central, first order derivative of f plus, and then we have the sign of the corresponding, but only the sign of the corresponding velocity component times the, that's also centered, 6f, and that's the derivative with respect to psi, this one's with respect to psi. If we just do it like this, then upbringing should work.
But I think that the sixth derivative here
Sorry,
is
there's probably minus, and there's delta x to the
actually is not good
and
if
there's
it,
a 1 to 60.
but actually is not good if the sixth derivative is cylindrical coordinates. It's not good if the sixth derivative.
This is a
No, no.
standard
The
sixth
point is
derivative.
that
Can
the
you-
real sixth derivative, for example, a semicolon and then 6 indices,
Yes.
is certainly not implemented in the cylindrical coordinate. But what Wolfgang is talking about is just a sixth order finite difference, just the way DER6 is. So he wants us to use that and just multiply that by 1 over r.
So remember this in the code.
Am I right?
For example, that's the one we have. That's the one you get if you use the routines that we so far have been using
We
for
just have
Cartesian
to
geometry.
edit DER6 a bit, because now if you call DER6, it complains that it is not implemented in cylindrical coordinate and dies. So
Yes.
you have to change that and
Yes.
multiply by the right factor of 1 over r.
But this is completely reasonable, isn't it?
Yes.
And this is, there's not even,
I don't think it's wrong at all.
I can't see anything that actually would favor the sixth order covariant derivative,
No,
or
this
even
should not be a,
motivate
this should not be a
expression.
covariant.
That's right, yes. So So we just treat this one in the correct way, which is done by doing this, which means just having a one-more factor. And we know how to deal with these things. We, as a code, we just do it's called y anyway, right? So we just do the hyperderivative in the y direction as usual, and interpret this in this way. And I might have to make sure that the one-more factor is in place, of course. It may not be, of course. That's probably not the case actually for the
So I was wondering if
as a part. So I think that's
that level that
good recipe then.
that's
Should we then stop here or any other comments for lunch?
but I don't have any
Okay, so then we stop for lunch and continue at 2 o'clock. And it seems I can actually lock the door here with my regular key. So I'm probably relying on this myself then, and leave my laptop.